In this lecture, we'll have a look at a particular example of the simultaneous equation bias. We will look at the structural equations, and from those equations, we'll derive the reduced form equations. And from these equations, it will become clear that running OLS on just one of the equations will result in a biased and inconsistent estimate. So the example I want to consider is a simple consumption function where we explain consumption using GDP. Beta 2 is the marginal propensity to consume. And so in this case, we have assumed that GDP is the one that affects consumption. But if we think about it a little bit more, we realize that we could just as well specify the opposite. That is that GDP is explained by consumption. Consumption is a part of GDP. So the higher the consumption, the higher the GDP. So there's clearly a simultaneity between consumption and GDP. If we just consider a small closed economy, to make the example as simple as possible, where we have no imports, no export, and no government, then the GDP identity will simply be the following. GDP is consumption plus investment. So these two equations, the second bullet and the fourth bullet, those are my structural equations. So here are my structural equations. Note that the first one is a linear regression model, while the second one is just an identity. This is just how a GDP is determined. So there is no error term in the second equation, and that's not meant to be run using a regression model. It has no unknown parameters. So let's derive the reduced form equations, and we can do that by just taking this one, which is this one, and plug that in here. So we have C equal to beta 1 plus beta 2. I have skipped this subscript I for convenience. It doesn't matter because each equation is valid for each observation anyway. So we have C plus I plus epsilon, which, if I open the parenthesis, is beta 2c plus beta 2i plus epsilon. Move this over to that side. Well, not that one, but this one. Then I have c minus beta 2c equal to beta 1 plus beta 2i plus epsilon. And this I can factor as c1 minus beta 2 equal to beta 1 plus beta 2i plus epsilon. And if I divide both sides by 1 minus beta 2, assuming that beta 2 is not 1, which makes sense, a beta 2 of 1 would imply that we have a marginal propensity to consume, which is 1, which would imply that consumption is all of investment. So if I divide by 1 minus beta 2, we get the reduced form equation for consumption, which is beta 1, 1 minus beta 2, plus beta 2, 1 minus beta 2i, plus epsilon over 1 minus beta 2. I can now plug this into the second equation, which was GDP is C plus I. So GDP is C plus I, and C was this one, plus epsilon 1 minus beta 2. That's C, and then we add I to that. So I have I here and here. So these two terms together can be written as beta 2 over 1 minus beta 2 plus 1 multiplied by I, if we factor out I. And this expression is just beta 2, 1 minus beta 2 plus 1 minus beta 2 over 1 minus beta 2, which is 1 over 1 minus beta 2. So these two terms together is 1 over 1 minus beta 2 times I. And then we have the other two terms. So combining this, we have beta 1, 1 minus beta 2, plus this 1 over 1 minus beta 2 times I, plus epsilon 1 minus beta 2. That is the second reduced form equation. It is reduced form because I have a dependent variable on this side. I have no dependent variables on the other side. Only an exogenous variable I. So this is the second reduced equation, and this is the first. So from the reduced form equations, it is now completely obvious that GDP is correlated with the error term epsilon, because it is simply partly determined by epsilon. A higher error term in the consumption function means that GDP is higher as well. And that in turn means that we go back to our single consumption function here in the structural form. These two variables are correlated. GDP is endogenous, and running this regression explaining consumption with GDP will give you biased and inconsistent estimates. So to summarize what we just did, we have the reduced form equations. We have this one for the consumption. Now we only have the exogenous variable I on the right hand side, and we had this form for GDP. From the second equation, it is clear that GDP is correlated with the error term. It's endogenous in the consumption function. And finally, estimation of the consumption function will lead to biased and inconsistent results. And this is an example of the simultaneous equation bias. Later on, we'll have a look at some methods for dealing with this particular problem of endogeneity.